Hey everyone, welcome to InsightsByRish. In today's video, I am going to implement a project of lung cancer detection using VGG16, that is a transfer learning method. And for that, I am going to make use of this particular dataset of lung cancer and the colon cancer histopathological images from Kaggle. I will provide the link of this dataset in the description box. Do check that. Now here we have the images for both lung cancer as well as for colon cancer, but we are just going to make use of lung cancer images. As you can see here, this entire folder is of 2 GB, in which we have in total 25K files, and we have two folders here, the lung image set and the colon image set. Now here we are just going to make use of the lung image set, which consists of 3 directories. As you can see, in the lung image set we have 3 categories. The lung ACS stands for lung adenocarcinomas, then lung_N stands for lung normal, and lung_SCC stands for lung squamous cell carcinomas. Now we have to classify that our image falls into which of these 3 categories. So now coming back to the code, the VGG16 is a pre-trained model on ImageNet, and we are going to make use of that model. So if you check the architecture of VGG16 on internet, you can see this image is from ResearchGate, and in this image you can see we have first 13 convolutional layers followed by max pooling layers, and then we have 3 fully connected layers here. The green layers are the fully connected, that is dense layers, and the blue layers are your convolutional layers along with ReLU activation function, and orange layers are your max pooling layers. Now this 13 convolutional layers along with the max pooling layers, this you are going to use. This blue layers, that is this convolutional layers, are called as bottom layers, and the fully connected layers, that is these 3 green layers, are called as top layers. So in our model, while building our model, what we are going to do, we are just going to freeze this convolutional layers, that is the pre-trained convolutional layers that can detect any kind of feature, pattern, shape, structure from the images, and we are just going to change the 3 fully connected layers, and we are going to add our own manually constructed layers there. So what will happen, it won't be computationally expensive, as we are just going to add 3 manual layers. So all the other convolutional layers are already trained, so there will be no training of convolutional layers, and hence it will be computationally less expensive. It will take very less space in RAM, and also the computation will happen really very faster. Now coming back to the code, there are first 2 mandatory things that you have to do while working with VGG16. The first is you always have to work with color images. VGG16 model is trained on color images, RGB images, that is on ImageNet dataset, and hence we can only work on color images here and not on grayscale. And the second thing is that the image size should be compulsorily of 224 by 224 pixels. If you check this image, you can see the first convolutional layer has the image size of 224 by 224 and 64 filters. So these are the 2 mandatory things that you have to follow while building any VGG16 model. Now coming back to this, as you know, this dataset is of 2 GB. We will not download it in our system. We will directly import the dataset from here into our Google Colab environment. And for that, what we are going to do here, just go to settings of your Kaggle and generate an API token from there. And once you generate that API token, you will get a kaggle.json file. Now when you get that file in your system downloaded, you have to put that file here in your Google Colab environment. So let me do that. As you can see, this kaggle.json is now placed in this Google Colab environment, and we are going to make use of this file to connect our Kaggle dataset in the Google Colab environment. Now that we have loaded this kaggle.json file here in our Google Colab environment, next we have to identify this file. We have to validate this file. So for that, let me write a code here, which is mkdir -p, then negation followed by Kaggle, that is our file name, and then again we have to say exclamation cp, then the file name along with its extension, that is JSON file, and then again the same thing that we did, negation and Kaggle. Let's run that. This code will basically identify our kaggle.json file, and now you can see it's successfully done. After that, now we can load the dataset here in the Google Colab, and for that what we have to do, we have to go back to our dataset, and then we have to copy the API command from here. After copying that API command, here you have to place that API command and you have to precede it with an exclamation mark, and let's run that. As you can see, the file is being downloaded directly in the Google Colab here itself. Now you can see the file has been downloaded, but it's in a format of zip file. You can see this lung and colon cancer histopathological images file. This is a zip file of 1.9 GB. Now what we have to do, we have to unzip it, and to unzip that we'll write a code here. So let's say import zip file, and here we will say a zip reference is equal to, here we have to place the path of zip file. Here we have to give the path of zip file. So let's say copy path, and let's place it here. After placing that path, now we have to also give the path where we have to extract that contents. So let's say zip reference dot extract all. We are making use of extract all method, as we want to extract all the contents from that. We'll say zip reference dot extract all, and here we have to place the path where we have to extract this contents. So we have to extract this contents in the Google Colab environment itself, and hence I will say content, and then we have to close this. So zip reference dot close. Let's run that. Now after that, just refresh your environment, and here you can see this new folder of lung colon image set has been now downloaded into your environment. Here you can see in that you have two folders of lung image set and the colon image set. Now what you have to do, just right click there in the environment and create a new folder here named as lung cancer. Let's rename it as lung cancer. And in this lung cancer folder, we are going to put the lung images, like the first folder of lung adenocarcinomas, then the lung normal and lung squamous cell carcinomas. This all folders we are going to place in our newly created folder, that is lung cancer. So we'll start with lung adenocarcinomas. After that, the lung normal, and then the lung squamous cell carcinomas. And here you can see now you have that three folders in the lung cancer directory. Now just rename them so that we will be having clear understanding here. So lung adenocarcinomas, then the second thing here, let's rename it to lung normal, and then the third thing here, let's rename it to lung squamous cell carcinomas. So after doing that, now what we have to do, here we have to create the categories and data directory. So let's say data directory, this will be our base directory, that is the lung cancer, and here we have to place the path of our base directory, which is lung cancer. So let's copy the path from here and paste it here, and then here we have to create the categories. Now these categories will hold the names of all these three folders, that is adenocarcinomas, normal and squamous cell carcinomas, and make sure that the name of these folders, that is this spelling wise, the names of these folders should exactly match with the names provided in this list, because if the names here in the lung cancer folder are different and here in the categories list is different, then it will basically throw an error. So in the categories, the first name that you have is lung adenocarcinomas. This is your first category. Then the second thing that you have is lung normal, and the third category that you have here is squamous cell carcinomas. So these are your three categories. Then we have to construct a path. By constructing the path, what I mean is you are going to extract every single element from this categories list, and one by one you are going to append that element with the base directory, that is your data directory. Let me name it base directory. So in the first iteration, you will extract the lung adenocarcinomas name, and you will append that to this path, with the help of which you will enter the lung adenocarcinomas folder. Same in the second iteration, you will extract the lung normal element from the categories list, you will append it here in the data directory, with the help of which you will enter the lung normal folder. So this is how we are basically going to construct the path. So let me run this cell. Now here I will say for category in categories, that is the list name. Actually, let me write it fully. So category in categories, here we will say path. Now path will be OS. So first we have to import the OS module here. So let me import that. Import OS. And here I will say os.path.join. And just provide the folder names that you want to join. The first is data directory, and with which you are going to join the categories. Now don't provide the categories list here, as you are going to extract the element from the categories list in the variable category, and then you are going to append that with the base directory. Hence here we will provide the category variable. Now after that we will say images is equal to os.list directory path. Then we will be extracting the images from this particular path. Now what we have to do, we have constructed the path here. Let me write here constructing the path. After constructing the path, let's say I want to display 3 random images from every folder. So we have 3 folders here. Let me say that I want to display any 3 random images from the adenocarcinomas folder, followed by any 3 random images from normal folder, followed by any 3 images from squamous cell carcinomas folder. To do that, we will make use of subplots. So let's say here, first we have to initialize the subplots. So we'll say figure.axis is equal to plt. Now here we have to also import matplotlib. Import matplotlib.pyplot as plt. And here we will say plt.subplots. Then in every row, that is in every row, you want 3 random images. That is, we will have 3 columns. Hence 1, 3. And then we also have to give the figure size. So let it be 10, 4. You will see how it works. After that, we also have to give the titles to every images. So we will say subtitle. Now here either you can give the titles manually, or we can directly give the categories that we are extracting as a title here. So let's say in the first iteration we extracted the adenocarcinomas category here, and the same category will be passed as a title here, so that we can easily identify that the 3 random images belong to which particular category. So I will do the same thing here. Let me say category, and let's give the font size here. So let the font size be 18. Now after that we will create a for loop here. So for I in range, and we want to display 3 random images, hence the range will be 3, that is 0, 1 and 2. Then we will say image name. Let's say the image name will be images, that is the images that we are getting from this path. Then we will make use of random module from numpy. So we also require numpy here. Import numpy as np. So we will say random np.random integer, that is randint, and we have to give the starting index and the ending index of the images. Now in the first folder we have something around let's see, in the first folder of adenocarcinomas we have 5000 files. In the second folder of normal we even have 5000 files there, and in the last squamous cell carcinomas folder we again have 5000 files. So the starting index is 0 and the ending index is 5000, and that is what we have to provide. So it will extract any 3 random images from that entire range. The starting index is 0, so let's say 0, and the ending image, rather than giving it manually, we will say length of images. Whatever the length of images it will be, that will be our ending index. This was the image name. After that we have to give the image path. The image path will be os.path.join. Now here you have to join the path along with the image name. And after that, let's say image array, it will hold our image data cv2. Now we also require cv2 module here, so we will import that. We require the cv2 module to read the images, to read the image data. So we'll say I am read, and here we will pass our image path. So this particular image array will read the images from this particular path that we are going to provide it here. And after that we will display the image in the for loop itself. So we'll say axis, that is ax, the variable that we have initialized for axis. Then at the location I, and I am show method. the image array. That is, we are passing the data of images with the help of which it will display us the images. And if you don't want your x-axis and y-axis to be displayed, then you can just switch off the axis here. So we can say x at I dot axis off. So it will switch off both the axis x and y. Let's run that. Let's see whether that works. Okay, the issue here actually it's not figure comma, it's figure dot subtitle, SUP title. Let's run that. And now you can see the images. You can see the first 3 random images from adenocarcinomas folder, and we have the same title that as the category name. The first category name is lung adenocarcinomas, and the same name has been given as a title here, as we have said the category as the subtitle. Then 3 random images from lung normal and 3 random images from squamous cell carcinomas. As you can see, these are color images. Even if you check the shape, so image array dot shape, you can see the channel dimension is 3, which means the images are RGB. Now, if you are randomly, now as we are working with a VGG16 model, we will keep these images in the RGB mode only. But if you are building the convolutional model from scratch, then there you might convert these images into grayscale in order to reduce the computation and the data. Now, one thing you can see here, the image dimension is 768 by 768 and the channel dimension is 3. The channel dimension 3, it's okay, but the picture dimension, the image dimension is 768 by 768. As I said previously, when working with VGG16 model, the first image size should be of 224 by 224. So the next task is to convert this image size and basically to resize the images. So here we will give a new image size, let's say image size as 224. And then we will create a new array in which we will store the data of our resized images. So we will say new array is equal to cv2 dot resize and pass the previous array, that is your image array. Now you also have to give the size by which you have to resize the images. So here you have to resize the images by 224. So you can either directly give here 224 by 224, or instead of that you can make use of that image size variable here. So image size by image size. So now this new array will hold the data for the resized images by the new image size, that is 224. Let's run that. Now if you want, you can even display the new image, that is the data stored in new array. So we can say plt.iamShow and just pass the new array. It will show you the first available image with the new dimension 224. So this is your first image. As you can see, now this image is very much clear and it can be identified easily. Though we have reduced the pixels dimension from 768 to 224, but if you reduce it more, like if you reduce it to, let's say, something 20, then you can see you might find some glitch, some blurring. See, you can see the image is not clearly visible. So depending upon your image size, the data also changes and the appearance of the image also changes. So let's make it 24 again. And now you can check the shape of your new array. As you can see, now it's 224 by 224 and the channel dimension is 3. So this is what we wanted to do to convert the image into 224 pixels. Now after that, we have to create our training data. So let's write here, creating training data. So here what we are going to do, we will write a function here of def create training data. Let's say create train data, and here we will repeat the same thing that we did earlier. Whatever we wrote here, we are just going to copy that, and then actually we don't require this. Now one thing you might have noticed that here we only have input data, that is we have the data for images, but we don't have the labels, we don't have our target feature here, we just have images. So we have to assign the labels to these images now, depending upon its category. Let's say label 0 for adenocarcinomas category, label 1 for normal category, and label 2 for squamous cell carcinomas category. So we have to assign these numeric labels now, and for that we will say here labels is equal to categories dot index. if you assign labels of object data type or string data type here, then in the later stage you again have to perform one hot encoding to convert them into numeric format. Hence it's better to make them in numeric data format right now itself. So we will say dot index and then category. Depending upon the category, the labels will be assigned. After that, we will say for image in os.list directory on that path, and this should be inside the for loop. Now here we will copy the same code whatever we wrote here of image array. The same thing we will copy it here. And the only change that we have to make here is inside parenthesis. Here we will say os.path.join the path and the image. Now after that we have to resize these images here in the training data also. So we will copy this code of new array and we will place it here. After that we have to append this input data, that is the image data of new array, and the labels along with that in our training data. So for that we will create an empty list here. Let's say training data. This is our empty list in which we will append our image data and the labels. So here we will say training data dot append the new array, that is the data for resized images, and then the labels. Now we can also put this in the try block. So let's say here try, and inside that we will put it, and the exception would be just let's say exception as e. We won't write anything in that, we will just say pass. So this was how we created the training data. We constructed the path, then we assigned the labels to every category respectively, then we created the image array, we reread the images from the constructed path, then we resized the available images to new image size, and then we appended the image data along with the labels in the training data list. Let's also call this function here. So we'll also call the function here of create train data, and let's run that. After that you can even check the length of training data. So let's say length of training data, that is the list, and we are getting only 5000 images here. Actually we should have 15,000 images here because we have 5000 images in every folder each. So I think the issue here the issue is this for loop should also be inside the previous for loop. So let's give a tab here and let's run that again. Now you can see you're finally getting 15,000 images. That is, we have 5000 images in every 3 folders, that is 5000 images in each of the folder. 5000 in lung adenocarcinomas, 5000 in normal, and 5000 in squamous cell carcinomas. So when you combine all of that, you get in total 15,000 images into your training data. Now we have to divide this training data into x and y. That is, x will hold all our input data and y will hold all our target data. As you know, this new array has all the input data, that is the image data. This will be stored in x variable and this labels will be stored in y variable. And for that we will create empty list here. Let's say x equal to an empty list and then y is equal to an empty list. Now here we will write a for loop. So we will say for features, or you can even say input, comma labels in training data. As you know that in our training data we have 2 things. First is our new array, which will be now getting stored in features, and second is the labels, which will get stored in this labels variable. And then we will say in x we are going to append the features, that is the input data, and in y we are going to append the labels. Let's run that. Now the next thing is, when you check the type of x and y, let's check the type of x and type of y. You can see both are of list types, but it's mandatory to convert them into array, and for that we will make use of numpy. And let's say x is equal to np dot array x and y is equal to np dot array y. So we are converting them into array. But there is one issue. This y is just an integers, that is the labels, and hence it can be directly converted to the array. But x data consists of our images, and hence it's mandatory to reshape them. So we will say reshape, and then here in reshape we will say -1, then the image size, that is 224, image size by image size, and then you have to specify your channel dimension. Now, as we are working with color images, that is RGB images, we will specify the channel dimension as 3. If you are working with grayscale images, then you have to give the channel dimension as 1. And this is how you convert the x and y into array. Let's run that. And now we need to check the type of x and y. Let's say type of y. You can see now they are converted to the array data type, and this is what we wanted to do. After doing that, we also want to divide them into training and testing set. So to divide them into training and testing set, we will make use of train test split. So let's say from sklearn.model selection, we will import train test split. And here we will say xtrain, then xtest, ytrain and ytest is equal to train test split. And here we have to pass our x variable and y variable along with the test size. So let's say we will divide our data set into 80-20 proportion, 80% data in the training set and 20% data in the testing set. So 0.2 will be our test size, and then random state is equal to 42. Let's run that. Now let us print the information about our training and testing set. So let's say here print. First we will print the length of our xtrain, that is the number of images that we have in our training data xtrain. So we will say xtrain length, which will be xtrain dot shape at 0. Then the second thing that we will have here, length. Now the second thing that we have here is the image size in the training set. So let's say xtrain image size, and that is xtrain dot shape. Now the image size will be located on index 1 and 2, and hence we will give the slicing here of 1 to 3, that is 3 will be excluded and only 1 and 2 will be included. And after that, at the end we will give the channel dimension. So we will say xtrain channel dimension, which will be located on the index 3. So we will say xtrain dot shape at index 3, and the same thing we have to repeat for testing set as well. So we just have to say here x underscore test, and let me change it everywhere. Let's run that. Now as you can see, out of 15,000 images, you have 12,000 images in your training set and just 3,000 images in your testing set. Then both in your training and testing set, the image size is 224 by 224 and channel dimension is 3 for both the set. So this is the information about the training and testing set. Now after that, what we have to do, we will actually start building our VGG model. So we will say VGG model building. And to build that model, first we have to import the necessary libraries. So first we will say import TensorFlow, STF, then from TensorFlow import Keras, and then we have to import the VGG model. So we will say from Keras dot applications, we have to import VGG. Let's run that. And let us build our VGG model now. Let's name it VGG itself. So we'll say VGG16, that is what we have imported. Then VGG16, and here we will take the weights from ImageNet. Now this model has been trained on ImageNet dataset, and we will take the weights of that dataset itself. Then the next parameter here is include top, that is whether you want to include the top layers or not. Now as I previously said, the top layers are your fully connected layers, that is the green layers that you are seeing here. This we don't want because these layers are trained on the ImageNet data. we are going to train it on our data, and hence we will only include the convolutional layers, but these 3 top layers are going to added by us, and hence we will say here include top is equal to false. That is, we don't want that top layers. And after that we have to give our input shape. So let's say input shape, it's image size by image size, and the channel dimension is 3. So you can directly give 224 by 224, or you can make use of this image size variable, and the channel dimension 3. So this is where we are loading the pre-trained VGG model. Let's run that. And as you can see, the data is getting downloaded here. Now, as I said previously, this VGG architecture has this 13 convolutional layers, and we have to freeze them. We don't have to train again because they are already trained, and we don't want to again retrain them, and hence we are going to freeze this 13 convolutional layers now. So here we will say freezing the layers. So here we will say for layer in VGG dot layers, that is a VGG is where we have loaded our model, and then here we will say layer dot trainable is equal to false. That is, we don't want to train them again. Let's run that. Now we have freezed this bottom layers, that is this 13 convolutional layers, and we have also not included this fully connected layers. So now it's on our part that we have to add this fully connected 3 layers here. So let's add that. Let me say adding top layers, and here we will say model is equal to keras dot sequential. First we will pass our VGG model here, that is the pre-trained model. Then we will pass a global average pulling layer here. So we will say keras dot layers dot global average pulling 2D. This is our next layer, and now we will add the 3 dense layers, that is 2 hidden layers and 1 output layer. So here we will say keras dot layers. The fully connected layers means the dense layers, and hence a dense. Now you can have any number of neurons in your first hidden layer, so let it be 124. You can change that number as well, and then the activation function will be ReLU for any hidden layer. So this was our first hidden layer. We can even add more. So let's say the second layer will have 512 neurons. So the 512, and these are our 2 hidden layers. Now the third layer will be our output layer. So we will say keras dot layers. Now the output layer is also a dense layer, hence a dense. And then now in our output layer, the number of neurons in the output layer will be equal to the number of categories we have. Here in our lung cancer, that is in our base directory, we have 3 unique categories: adenocarcinomas, normal and squamous cell carcinomas, and hence we will have 3 neurons in our output layer. And then for multi-class classification, the activation function will be softmax. So this is how you add the top layers on the freezed bottom layers. Let's run that. Now after that you have to compile. So you will say model.compile. Then the optimizer would be Adam, that is currently the best available optimizer. Then the loss function. Now as we are performing multi-class classification, the loss function would be categorical cross entropy, that is the target variables are in the format of 1 hot encoded, then you just have to say categorical cross entropy. But in our case we haven't 1 hot encoded that, and hence we will say sparse categorical cross entropy. So sparse categorical cross entropy. And third, the metrics, that is on the basis of what you have to evaluate your model. So we have to evaluate our model on the basis of accuracy. So this was the code for compilation. Let's run that. And now we finally have to write the code for fitting, which is very easy. Just model.fit and supply your training data here, xtrain, bytrain, and specify the number of epochs. Now always start with less number of epochs. If you are satisfied with what accuracy you are getting with that number of epochs, then keep it as it is. But if you are not satisfied, then you can increase the number of epochs. So we'll say epochs is equal to 5 right now. And before running this, let me also inform you, when you just run this with the normal runtime, that is the normal CPU runtime, then it will take a lot of time, and hence we have to change the runtime type here. So just go to runtime and select change runtime type, go to T4 GPU and save that. Now we will connect to a T4 GPU runtime type, which will make our computation faster. But due to changing the runtime type, now we have to rerun all these cells from starting because we have lost all our progress. So we will just start. So we will run all the cells again, and we again have to load that kaggle.json file here in our environment. As you can see, the progress in the Google Colab environment has also been deleted. So I have again placed that kaggle.json file here in the environment, and I will again run all these things. And now you can see we again have to create that new folder here named as lung cancer because all our progress was deleted. So lung cancer. Then we will again place that lung cancer images in that folder: adenocarcinomas, normal, and squamous cell carcinomas. And we also have to name them. So let's just copy it from here. We will run this, and now we will run all the cells. Now you can see the training has been started. So here we will just write the code for evaluation, that is loss comma accuracy. Till the time it's running, we will write the code model.evaluate. So we are going to evaluate the model on the testing set here, that is xtest comma ytest, and here we will also print the model's accuracy. You can see in the first epoch itself the accuracy is 93%. So when you are getting the good accuracy by just using less number of epochs, why go for high number of epochs, right? So just always start with less number of epochs, and then depending upon the accuracy you can change the number. As you can see, at the end of 5th epoch the accuracy is 98%, which is really very good. But this accuracy is on our training set. We also have to evaluate the model on the testing set as well to check whether the model is overfitting or not. Then here we will multiply the accuracy by 100 to display the accuracy in the percentage format. Let's run that. Now as you can see, you are getting an accuracy, a very good accuracy of 97% on your testing set as well. And there is no drastic difference between the accuracy on the training set and testing set, which means the model is not overfitting. And this is working completely fine. So when you make use of VGG pre-trained model, you get very high accuracy because it's trained on very large amount of images. So we are getting 97% accuracy. Now we will also print its classification report and confusion matrix. So before you go ahead, you also have to make predictions. So let's say model.predict for xtest. Let's run that. Now as you can see, you are getting a series of accuracies for a single instance. For every instance you are having 3 probabilities of accuracies. That is the one having highest probability is where the image belongs to. But this is happening because we have used softmax activation function in our output layer, and hence to get a accurate appropriate label of prediction, what we will do, we will make use of numpy here. We will say numpy.argmax. So what it will do, it will check the index at which we are having the highest probabilistic value. The index at which we are having the highest value, that index will be our label. So let's run that. So right now it's just showing one single value, but we have to store this in a variable called as spread. So let's say, and then the prediction for every instance will be stored. So let's say pred is equal to, let's display the pred here. and as you can see, it's still making a single prediction, and that is because we have to reshape it. So here what we have to do, we have to say axis is equal to -1. Now let's run that. Now you can see that we are getting a series of predictions. That is what we wanted. Now let us compare it with the true labels. The true labels are stored in ytest variable. So let's say ytest, and let's display the first 5 true labels here. These are the first 5 true labels. Probably the 0 label has been assigned to adenocarcinomas, the first category. 1, the label has been assigned to the normal, and second label has been assigned to the squamous cell carcinomas category. Now let's see what our model has predicted. So let's display the first 5 predicted values. As you can see, the true labels and the predicted labels are exactly same, which means the model is performing really very well, as we are having an accuracy of 97%. Now we will plot the confusion matrix and the classification report. So let's say from sklearn.metrics we will import the classification report and the confusion matrix. So let's first display the classification report. And here you have to pass your true label and the predicted label. The true labels are stored in ytest. So let's say ytest, and the predicted labels are stored in pred variable. So let's say pred. Let's run that. And as you can see, you are getting an F1 score really very good for every category. If there is drastic change in the F1 score value for the different categories, then you can say that you have an imbalanced data set. But here the data set, each category has 5000 images, which is equal in numbers, and hence the F1 score is good for all the 3 categories. Even the precision and recall values are good. Now we will plot the confusion matrix. So let's say CF is equal to confusion matrix. Let's pass the true labels which are stored in ytest and the predicted labels which are stored in pred. And let's say normalize is equal to true, as we want to display our values in percentage and not in count. Then to plot this confusion matrix, we require cbun. Let's import that. So cbun as SNS, and we will make use of heat map to plot the confusion matrix. We will pass that CF variable. Then anode is equal to true basically means we have to display the values on the grid. And then cmap, that is the theme of your heat map. You can give it anything. Let me say crest. Let's run that. This is the confusion matrix. Let me also give the labels here. So plt.xlabel. On x-axis we have predicted values, and on y-axis we have actual values. So plt.ylabel actual. Let's run that. So as you can see, the diagonal, that is the dark blue squares, are showing the percentage for correct classification. So your diagonal, that is the dark blue squares, shows the correct classification accuracy. When you take the look at the first coordinate, let's say 0, 0, that is 0 on x-axis and 0 on y-axis, you can see the value 0.94. The first category 0 is for adenocarcinomas. So which means the classification of adenocarcinomas is happening with 94% accuracy. While when you take the look at coordinate 1, 1, you can see the accuracy is 1, that is 100%. That is the normal images are getting classified with 100% accuracy, correctly classified with 100% accuracy. And the 2, 2, that is the squamous cell carcinomas images are getting classified with again 100% accuracy. So as you can see, the accuracy is really very good, and even the model is performing good, predicting the values which are closer to the true labels. So this is how you make use of pre-trained VGG16 model in order to build your convolutional neural network, so that you don't have to build the convolutional layers here. You can just put the top layer, that is the fully connected layers, on the bottom layers, pre-trained bottom layers. So that's it for the video. Thanks for watching.